Welcome. I'm going to be running a workshop that covers the simulation side of running CARLA, ROS, and Docker together to utilize these for simulation applications. To begin, I would like to discuss first with why this is important and why this application is useful. So, in the case of building autonomous vehicle systems, there's a couple of factors that limit progress on this vehicle. For one thing, you have the weather. Oftentimes you can't control the weather, and if the weather conditions are bad, you might not want to test experimental systems that haven't been evaluated on it. Further, it's hard to coordinate when certain weather conditions are around and when you want to test for those conditions, for example. So overall, the weather is very undeterministic and doesn't help with your testing. Next is to actually go out and test with the vehicle. Requires maintenance, and in particular in the case of UWAFT, the other sub-teams may be working on the vehicle as well, and it might be offline, so you can't even physically use the vehicle during those times. Lastly, it just takes time. If you want to go out and run a physical test on a vehicle, it takes a lot of time to just get everything ready, go out, actually do it, and then collect the data from the vehicle and everything. And so all these factors make real-world testing on a vehicle for automation systems and CAVs altogether much more difficult. And so what we want, or what the need is here, is we want to develop and test software without conflicting with the rest of the team in a controlled environment. And one way to achieve this is to leverage simulation and software tools that can automate the testing and also parallelize development. And so this is why we want to leverage a simulation infrastructure, so we can run tests in parallel in very controlled environments multiple times, and the barrier and access to run those tests are much simpler than having to go out and physically test on a vehicle. To do this, there's a couple of things we want to leverage together, and we'll discuss each of these individually. First is Docker, which is to just containerize our applications and make them deployable. Next is CARLA, which is the kind of simulation infrastructure itself. And then we want to integrate with ROS, as a lot of the algorithms and sensor systems will be built in ROS. And lastly, Foxglove is a application we can use to actually be able to debug and visualize some of the data generated by ROS and CARLA together. So to start with Docker, this is a software platform that allows people to create containers and run applications in a container, which is essentially a little bucket that isolates it from the host system and is independent from it. And the reason why containers and Docker in particular are useful is because, one, they're portable. So as it mentions here, it's platform agnostic. So once you define a container, it can run on any system, and it's not constrained to the specific environment on that system. Next, it's efficiency. Overall, it's lightweight and much slimmer than most traditional virtual machines. And it's also easier to make much more slimmer and lightweight than virtual machines. And you can kind of scale up and down how large these containers are. Consistency. So essentially you define a specific Docker container in a Docker file, which makes it so that the application is built in a repeatable and consistent way. It makes it programmable, which makes it easy to track through revisions, and also very deterministic as to what steps happen when it's being built, and it's all controlled and tracked. The isolation provides a sufficient level of isolation from the application host system, so the environment on the local host system does not conflict with the application. You can configure a specific environment for the application in the container, and this helps with portability and just all that. And also, if anything goes wrong, it's all contained in the container as well. It doesn't spill out to your host system. And lastly, it's very scalable, so it's very easy to just start deploying more containers horizontally if you need to run more instances of something, or if you want to deploy a whole cluster of services together, you can define how that is played out. And for these reasons, this is why Dockerizing certain tools and applications is very practical and useful, especially in this particular case. Next is CARLA. So this is the open source platform specifically built for testing and developing automated driving systems. And it offers a semi-realistic environment, so you can play with realistic physics. You have weather conditions and different urban environments you can test with. Because this is running in a simulation, it's safe and cost effective. You don't have to go out and run real-world testing with this. It supports all kinds of sensor simulation, such as LiDAR, radar, and cameras. And also it's open source, which makes it very extensible and accessible. You can customize it to your specific needs as well. Next is ROS, which is a general open source framework for building robotics. And ROS is popular and useful because it's modular again. And it's overall built on a very modular concept of defining certain nodes, where each node can run independently and run together, and they can share and communicate in specific ways. Its flexibility allows it to essentially run on various different hardware and software platforms, so it can run on all sorts of devices. It's got a large community, so there's a lot of just good community support for it and examples and development and research that you can reference. And with the community support comes a large suite of tools and libraries to visualize, build simulation environments, test software, all that sort of stuff. And it also comes with the same benefits that open source that was mentioned previously. Lastly is Foxglove. This is another open source platform that it essentially provides an additional suite of tools and libraries that assist in particular with ROS. And it's very simple, so it just makes it easy to build. Again, with the modularity, allows for good customization. It functions in real time, so you see real-time data and logs coming in. It's well supported again. It's deployable on many platforms and in various different forms. And once again, it benefits from the same open source benefits as mentioned before. And so with all these systems mentioned, this is what we're essentially trying to build in the simulation stack. And this is an example from the autonomous vehicle team, Autonomous. Effectively, we want to be able to have some server cluster that we can access as developers, as you see here. And on that server cluster, you're able to run Dockerized containers of each of these different services. So you have CARLA in a Docker container. You have the CARLA ROS bridge, which we'll explain later on, but essentially it translates CARLA messages into ROS topics so that other ROS nodes can view them and see them in a native format. Any sorts of other modules that we want to run, such as detection, object tracking, mapping, all these sorts of other applications that you want to run. And then any sort of sensor simulation code, and also interfacing with potentially physical sensors. And into this stack, CARLA fits into the front-end software modules. And you can run multiple different ROS containers, each doing a specific application. And this can be hosted on the server or locally, and then there's multiple ways to deploy it. And it makes it very extensible, and that way you can develop locally on the server, SSH in. You can deploy one of these modules or many at the same time, and it's just very configurable. And with what we just mentioned, this is kind of the top level architecture of what was built and what we'll be demonstrating later on. And right here, the current configuration you see is assumed to be running on the server, where the user can SSH in and then access and deploy all these containers you see on the server. And so we have our Dockerized CARLA instance. There's the ROS bridge, which essentially transcribes CARLA into ROS topics. There's the Foxglove bridge, which essentially monitors all of the ROS topics and is able to then forward them through WebSocket to Foxglove, which then does the GUI and visualization and also provides the logging and debug information. Then we can run Docker containers that contain individual ROS nodes or Docker containers that contain multiple different ROS nodes. And then lastly, we can also run CARLA clients, which use the CARLA API interface with CARLA directly. And so all of these are isolated. They can be run in different configurations, and they can also be run together, as you've seen here. And this is what we're building towards. So for this workshop, we're going to do a quick overview of Docker, so you're familiar with that. Also look at Docker Compose. Then we'll specifically look at running ROS and CARLA with Docker. We'll take a brief look at Foxglove, and then the remainder will be actually deploying the whole stack in different configurations and walking through that. It is assumed that you have some knowledge of what ROS and CARLA involve. Docker will take a deeper dive into, and Foxglove will also take a little bit of a deeper dive into. Now, as we get started, just a little to let you know, this will be linked in the description and everything. All the code is situated here at this repository, and there will be links provided. It's strongly recommended you clone this repository, as we will be using many of the examples in here going through the workshop. And there's specifically a workshop folder that contains a transcript of the entire workshop and what we'll cover for you to reference, and also contains some resources and information about the workshop as well. So the slides we covered previously are available here as well for your reference. And with that, we shall get on the way. So yeah, as mentioned in the intro, slides are available here. Be sure to clone this workshop by running like the following command here, get clone. There's a URL, links will be provided. And a couple of things to note as we're getting started here is that this is we're going to be running this on a Linux system, in particular Ubuntu. It is recommended to use Ubuntu/Linux for everything you're about to see. However, most of this stuff is Dockerized, so it should be replicable on any OS. And then it's also assumed that you have at minimum Docker and Docker Compose installed, along with access to the autonomous server cluster. If you do not have Docker, if you do not have any of those set up, then if you go into the top level directory here, and if you look in this README, the first summary talks about Docker. There's the getting started guide, and then this guide on how to set up and install it. And then same with Docker Compose, summary, set up and install, and everything. And then if you scroll down a bit more, there's guides on everything we're about to cover here as well. And there's also a guide on how to access the autonomous server cluster here. So in short, this top level README has very specific and verbose information, everything contained in this repository. So feel free to use this for information. And you feel free to use this for the setup and install steps. And then we'll be starting off with the workshop specific content, and then the workshop will transition to covering some of the other stuff in the rest of the repository. So yeah, just keep that in mind as we move forward. So now to begin, we'll discuss by just going over Docker. And as I mentioned before, everything I'm about to cover, you can just follow in the workshop README as is. With that, we're going to navigate over to the terminal. So the first thing to do is just to make sure that if you have Docker installed, just run Docker. You should be able to see just the list of commands you can run, and if this pops up, you know you have Docker installed successfully. You can also run Docker -- version. Also another way to check if you have Docker installed properly really quick. And one of the key things to keep in mind is if you run some commands such as Docker or something and get some error along the lines of command not recognized, service not available, something along those lines, you might need to actually start the daemon, and then on a Linux system, in particular Ubuntu and Debian, you can start the Docker daemon by running this following command. So if you see this, something like this, when you run docker -- version, or you see these commands when you run Docker, it means the daemon's already started. If not, try running this and then see if that fixes it. So that's a little aside. Typically, the Docker daemon will start automatically. However, that might not be the case. In any case, once you have that confirmed, we'll start by covering Docker plus, and this command is essentially just lists the running processes. That specifically lists the current running processes. And now we can see that nothing is currently running. And so this is a quick way to just check what is running on your system with Docker specifically. If you do Docker /a, then this will actually list all the containers that is available on your system. And right now, currently, I have nothing. I actually just cleared out all my containers previously, and I have no containers loaded up on my system at all. So we'll come back to this later, but I just wanted to start there. Next, you can also run Docker images, and this actually shows you all the images that you have downloaded on your system. As you can see, there's a ton of stuff here, just because I've been building a lot of Docker containers and whatnot. But if you go down here, relevant to our discussion, you can see I have a CARLA ROS bridge image here, ROS2 container, CARLA client, Foxglove image here, CARLA image here, some ROS images, for example, so specific distributions that you can see in Humble. So you can see all kinds of images that are present here and downloaded. So with Docker, when an image is one thing, that is essentially the base code that defines what the container looks like, and the container is essentially like a running process of that image. And you can use images as base to build other images, custom images that you can run as containers later, and we'll be discussing more of that later. So to show an example here, we can pull the hello world container by running docker pull hello world, and I already have this downloaded, so it's available. It'll download for you. And then, for example, if you run Docker images, then you should be able to see the hello world container. And as you can see, I have that right there. And we were speaking earlier about Docker and how its size can be very efficient. You can just see here from this list of these bottom couple of images that I have, we're ranging from 13 kilobytes for the hello world up to 150 and 154 for this CUDA, NVIDIA, and Python stuff, 470 approximately for Kafka, and then CARLA up here is almost at 17 gigabytes. So as you can see, they can range in sizes quite a lot. In any case, we have hello world downloaded, and now we can run hello world. So to run a container, you do docker run, and then you do the you can do it by ID or by image name. So we'll just do it by the name here, hello world, and then you get this little printout here as the hello world for Docker. So that's just a quick little example of like pulling a container from the Docker registry and then running it. And if you don't know what Docker registry is, if we go here, Docker registry, or Docker Hub as it's known, and let's just go Ubuntu here. You can pull all sorts of images. So here, for example, is an image for Ubuntu and all sorts of other variations and whatnot, as you can see. So everything that I'm pulling here exists on some sort of registry, such as this, downloading it and running it locally. So that is that. But now what we're going to do is we're going to define our own little custom image. So if you've pulled the code from GitHub for this whole project and gone into the workshop directory, as I'm in here, you'll see there's this folder called app. So we're just going to go into the app folder, and then in here there's an example of a custom Docker file. So we're just going to open that up. I'm using NeoVim here for this. You can use whatever editor or system or software IDE you'd like. And in here you can see that what I'm doing is I'm using the base image Python 3.7-Alpine. So this is an image that exists on like Docker Hub, for instance, as a registry. So I'm pulling that and using that as a base image to build my custom image, which I can then run as a container off of. So, for example, if we go back to running Docker images here, you can actually see, should be able to find it, Python. I have 3.9 Alpine here. Where are you? Okay, I guess it's not stored, but here's an example. I have the 3.9 Python Alpine image here. So for this container, I'm using the 3.7. In any case, so I'm using that. It has Python installed on it. And this is a lightweight container. That's what the Alpine is for. It's using a very lightweight version of Linux. And then I won't go, just specifying a work directory here, not anything too important. And then what I'm doing here for this very simple image is I'm copying over this specific app I have built here and copying it into essentially the image and / container here as well. So like think of it as kind of two buckets. Your host system is one bucket, and then this container / image is the other bucket. And then I'm taking this app that's defined in the host here and copying it over into the image so it can run there. And as you can see, that app is available right here. And this is just a very simple Python app, like stupid simple, that just prints out stuff and sleeps for a little bit just for demo purposes. So that gets copied over, and then we run this command to actually run that, and that'll just run continuously. So here's an example of defining a very, very basic Docker image, a custom Docker image. And then so once that is defined, we can build that running this command. And here I'm specifying a tag just so it's easier to reference afterwards, essentially giving it a name that I can use to then run it and tag it with afterwards. And this dot is just to specify build what's in this current directory. And this will just look for a Docker file and then just build the called Docker file and just build that. So we run that. It's going to take a little bit to build here. And now it's done. And then what we can do is I can run the application, specifying it by the tag you see here. And then I can actually just run this. And then you'll see it's right now running the container right here and printing out the output as is. And then we'll just hit Control-C to exit out of that. Now if we run Docker images, you can see simple Python app is right here as one of the images we just built. As you can see, size of 47 megabytes, very, very small. And then if we go back to running docker-a, you can see now that this is a container I have created, right? So you can see that exists here. And then we can also run this by container ID, for example. So if we go back here and paste that in and run it. Oops, my bad. I guess I was mistaken. Actually, I think it was. Where is it? Yeah, there you go. I was sorry. It wasn't container ID. You can also run it using that image ID from what was built there. So that is how to run a simple container. Now, if we run this again, I'm going to go back to running it using the tag right here. So if this is running, we're just going to open up another terminal here, and this is still running. And then so you can see when we run Docker now, it's actually showing the running process. So it tells you how long it was created, how long it's been up for, and all this information. And so you can see this is running. You can also run something like Docker stats, which then gives you a live time summary of the CPU, memory usage, all this sort of stuff, which is good to track when you have a bunch of stuff running that's more intensive, for example. So that's also something you can run. So yeah, it's running right now. Docker Compose does show it executing. If I go ahead and stop this, and then I run the same command again, and I can see nothing shows up because that container is not running. If I run the -A, this just lists all the containers, and I can see how it's spun up a new container when I run that, and that exists there. So that's that. And then lastly, if you run this again, and then if we go over here, if we run Docker, let's say this is, you can run this in the background, so it's not displaying the output here and to give space in the terminal, for example. Then if you have a container running, such as here, as you can see, you can also just grab the container ID, and then to stop it, you can run Docker stop, place that in there. Oh, there you go. Just took a second. Sorry, I got a little worried there. I was thinking of the wrong thing. No, but there you go. So there, it stopped it. Just took it a little second. And yes, that's how you can stop a running process that is running somewhere in the background, for example. So hopefully that gives you a little bit of a idea of how to run and manage Docker containers and how you can build one from scratch. And as mentioned, all of this that I just covered is summarized in the Docker overview section of the workshop README. So next, we'll just cover Docker Compose, which added some additional functionality. And again, everything I'll talk about is available in the workshop README. So as mentioned before, if we go over here, you can quickly check if you have Docker Compose installed properly by running Docker Compose. It'll list all the commands that you can run with it. You can also do Docker Compose -- version right there. And then just to verify that it is properly installed. Once you've checked that, I'll give a little bit of an explanation of the usefulness of Docker Compose, and it's easily summarized here. Essentially, it's very useful for running multi-container applications and allows you to configure network and container settings, and allows you to do it programmatically. So essentially, you can just define a file which will be defined in the YAML format, and this will store all those configurations and settings. And then you just run one simple command, and it'll kind of orchestrate building each container, linking networks, doing all that stuff. So allows you to define programmatically what to run and execute and how to execute it together, and then you just run the command and it just does it for you. So it's very useful for deploying multiple containers together, and also just like remembering what settings to run something and tracking that through the code. So, we'll go back to the workshop folder here in the repository. So you also see here there is a server folder, so we're just going to go into that. And then in here there's a couple of things you'll see. So first, I just have defined a simple Flask server here with one endpoint as for demo purposes to use as an example. Next, there is a Docker file here that to just run this application in. It's very straightforward. It's almost the same as what you saw previously, except there's one more step where we're installing Flask into this container. So I mentioned before the benefit of this is isolated from the host system. And this is an example of how you can, for example, in the case of Python, configure a specific Python environment or any environment in general inside the container that's completely independent of the host. So we're installing Flask here, and then this is what we're using to define our custom image. And then we have a Docker Compose file here. And then so if we open that up, this is kind of the structure of a Compose file. You do need to specify a version. This is more important than you might think. Just standard, just do version 3, for example. And then you can define each of your services individually. So we're just calling this app. This is the service name right here. You can define that as whatever you wish. And now you can define the actual list of commands and settings essentially to run for this. So here we're defining what image to build. So this is set up right now to build the local image that's present in this current directory, and is looking for the specific Docker file. It's just like called Docker file here. So this is steps on how to build this image. We're giving it a very specific name. This is just useful for later. So when we want to call it and reference it, we can reference it by this name. This is just another setting that says if it crashes, the container crashes, if there's some process running in here, like for example, if this server tries to run but falls some sort of segmentation fault, it will restart the server and keep restoring it. You can have this configured so that if that happens, the container shuts down, goes away. And they're also doing port forwarding. So we're mapping the port inside the container at 5050 to be exposed, so you can access the port externally from the container at the same address. Typically, ports and networks are isolated, so it only exists inside the container. However, you can expose specific ports just like here. You can expose the entire network to the host. There's many ways you can configure it, but this way we're at least exposing this one specific port that in our case is what this server is running on. So here we have a server, it's running on port 5050, and that means we want to make sure that the container has that port available outside of it so we can actually interface with it. So that's how you define a Docker Compose file. And to build this, all I have to do is run Docker Compose up. And that'll create it. This is just a Flask warning, so don't worry about that. And then you can see that the server is active. It's running here. You can see it's running right here. And then since that port has been exposed, what we can do is we can just navigate to a browser. We'll do localhost 5050, and you can see there is our endpoint right there. Hello from Docker. And right now we're running the Docker Compose in attached mode, so it actually prints out the logs of the container here. You can see the container name and the logs it's printing out. We can run Control-C to shut it down, as was done there. Another thing to note is we can also run this in detached mode by specifying -D, which is often the case. You'll often run it in this mode because it doesn't kind of like bind to the terminal and list all the logs there. So we'll just start it up, and now it's running in the background. Now if we run Docker, you can see that this is running right here. So it's been up. We can run this again. You can see that updates, and then we can still access this endpoint from here. And we can also run the same commands as before. So we can run Docker stats here. And you can see it's running there. You can have very little CPU. And yeah, so we can run all these the previous Docker commands we discussed with Docker Compose. Docker Compose is just another layer to kind of coordinate running different containers together and specify all kinds of different configurations. Now we'll discuss how to run ROS in Docker and with Docker specifically. One thing I'll point out is that for the remainder of this workshop and all this stuff we'll walk through here, it's not going to be running stuff contained in the workshop folder. It's going to be running stuff contained in all the other folders that are available in this project. So just be aware of that. And I made a mistake clicking on it because it's taking forever. There we go. So we'll be using other stuff located. So specifically for some of this compose stuff, we'll be looking at some of the compose files and scripts defined here in scripts. So just wanted to highlight that. So you are aware. With that being said, let's go back to the terminal here. And then let's just go back to the top level folder here. And now let's cd that scripts folder. And so here we have a couple different Docker Compose files defined. And specifically, we have this ROS2 nodes demo defined. And so if we just take a peek here at what's going on, essentially it's just defining two services, one called talker, one called listener. And what this is doing, it's just pulling this specific Docker image, which I think it's Open Robotics Foundation, something like that, Open Source Robotics Foundation, the people who create ROS, have provided for all their specific distributions. So here we're using Humble for this example. And so we're just pulling that container, and then that container actually contains some sample code, some sample nodes. And so we'll run one of the sample nodes, which is the talker node, and then we'll also define another service which uses the same base image. However, it's going to run the listener node. So here is one container running one node, which is talker, and another container running another node, which is listener. And here we also explicitly said that this depends on talker. So this container will be built once talker is built and running successfully. So that's an example of like the ROS container and images that are available you can pull. And this is a way to just pull and run some of the base code that already exists on it. So just for demoing, we will run those by running the following command. Since this name is not specified as Docker Compose, we want to specify the file name as follows. And so we'll just run that. And so you can see here, talker and listener talking and listening to each other. And that's just going to continue on forever. And so that's an example of those running ROS. And then so each of these are running ROS nodes, and they're communicating across both containers together. And the nice thing about Docker Compose here is it links the networking of these two together, which is why they can see the different topics and communicate with each other. So I'll just let this finish removing those. But you probably, if you're developing in ROS, do not want to just use the baseline ROS examples and code that is provided. So what we'll do now is we'll just go back out to the root folder, and now we'll go into this folder here in Docker. So here we have defined if you will, a custom ROS2 container that contains a customly built node. So as you can see here, we actually have a ROS2 workspace defined here. So which is a full-on ROS2 workspace in here. And if we just go, and you can see we have some nodes and packages defined in here, for example. So that can all be defined locally. Then we've also defined a Docker file, which essentially takes this base container image, as you can see, and then we're going to have to install. First, we're configuring the shell to use bash. We're going to install some extensions here, and then we can copy over the entire ROS2 workspace. So this will copy all that over on the little code there, and then we can cd into it, source the ROS Foxy setup, and run colon build to actually build what we have in there, and this will build those nodes inside of the ROS container and kind of bake it into the image. And then specifically for running ROS in a container, you want to copy over an entry points script, which we'll look at what that does in a second. And then we're going to use that as the entry point. So this functions similarly to command as before, except it's just going to run this once when the container gets initialized. And so this is the basic outline of the basic steps you need to define a custom container for running ROS. And so just to show you, oops, this is ROS entry. There we go. Yeah, this is just a basic entry script. All it's doing is just what you would do normally manually when you're trying to set up the ROS environment, source the distribution or release you want to use, and then it's also just going to run the setup script for that workspace as well. So this is something you're going to want to have, and then you're going to want to add that to your Docker file, and then as we do here, copy that over and then actually run that. And this is something specifically you're going to need to do for ROS running in Docker for whatever Docker file instance you set up. So in any case, we have this workspace, we've copied it over, we defined it, and then we can now build this container running this command. Take a second to build here. Yeah, and that is all built. And then as always, you can just check Docker images, and we should be able to find it here, ROS2 container. Yep, that's just been built here. And then now we can run that using this command. Now, here we're going to do something a little different. Before, when we ran Docker containers, you just ran it as is, and it kind of run in the background. Here, this -it is going to run it interactively, which essentially means that we're also going to run a shell inside the container. Here, specifying we're running the bash shell, and then this way you can kind of go into the container and run stuff from there. So, for example, if you don't have ROS2 installed on your system, you can define this ROS2 container that we defined here, and then you can just run it interactively, and then you can actually run ROS2 inside of Docker on your system without having to have ROS installed on your system. And I think just for demo purposes, let's just do ls opt ROS here. So you can see I only have Humble defined on my system. But as you can recall, in this Docker file, we're actually using Foxy for this container. And so if we run this, now we're actually inside of that container, as you can see here. And then if we run ls, you can see there's a bunch of stuff. But as you can see, there's that ROS workspace we just copied over. There's the entry point script, and then we can do what was it? Print env ROS distro. There we go. As you can see, and it tells us it's Foxy. So now I'm able to use Foxy on my machine that doesn't have Foxy installed because I'm running it inside of a container. So this is a nice way that you can set up ROS, run it, play with it without having to actually install it on your system. There are some downsides, but we're not going to cover those right here. And so actually cd into that ROS2 workspace we just copied over, and as you can see, it's all there. And then we can actually run one of those nodes that are defined. So we can go here, and we'll run this node that's already been predefined there. And it looks like there is an issue. We'll be back. Sorry. Yeah, that was an interesting error I ran into there that I've been encountered before. Just redefined how the example ROS2 node that was built for this example was defined and written. So just made a small little tweak there. So now things should function as expected before we ran into that little nice surprise. So yeah, I'm here back in the container running a bash shell. We'll cd into the ROS2 workspace, and then we can now run this example node. So that will just run, and this is just going to print out whatever topics are available. There's not much going on right now, so it's just a standard ROS out and then parameter events, and that's just going to keep looping through and printing out all topics available. But that's just an example of running a custom built node, ROS node in this container, in this defined ROS2 container. And then to just leave that, we just run exit, and now we're out of the node. And also, yeah, you can see that this is this container, this ROS2 container, is not up anymore. Actually, while we're here, I'm just gonna stop this one. There we go. So we're all clear. But in any case, that is how to run and use ROS with Docker. So now I'll walk over how to run CARLA with Docker. So for that, we're going to go back into the root here, and then we're going to want to go into the scripts folder. And in here, we have this CARLA Docker file defined and built that can run CARLA by itself. So let's just open that up and just take a look. So here it gets the CARLA Docker file. So the CARLA simulator does have Docker files defined for specific versions of CARLA. So we're going to build that. We're going to set up this command to run it. And then we're also, for this specific demonstration, we're going to output the display to the current display so you can actually see what's going on. So this is a simple Docker Compose to run and build CARLA. So if you don't want to install CARLA locally, you can use this Docker Compose to run it inside of a container. And so, same as before, we're just going to do Docker Compose up, but we're going to specify that file here as is right now. And that's going to run that. And then here we have CARLA simulator loading up. Just going to give it a second. It's a pretty large thing, so it actually does take a little bit of a minute or two to get loaded up here. And there we go. So CARLA is running, and now you can't see my cursor, but actually if we go in here, I can start moving around and playing around with CARLA simulator. And this is all running inside of Docker. So here's a way that I can use CARLA Docker. And then now, if I wanted to, I could use the Python API and specify this server and tell it to run certain simulations and examples in here. And we'll briefly look into that a little bit later. So I'm just going to exit that out. That's going to shut down there. And that is all there is to it. So that's just a very simple way of running CARLA using Docker. And in the README that is defined at the top level of this project here. If we go to the CARLA section, it does actually cover also another way of doing it directly without using Docker Compose here, but this is the most straightforward way. So that is pretty quick, nice and short. Lastly, we'll just cover Foxglove. So we talked about Foxglove before. It's a tool that we can use to visualize the ROS data and also get the logs. And so if we're here in our scripts folder, first we're actually going to run this ROS2 nodes demo, just so we have some containers, some ROS containers and nodes running in the background that are printing out something, just to make this interesting. So I'm going to run that. Next, for Foxglove, you want to run the Foxglove bridge, which is a very simple Docker Compose here. And what this does is it just essentially takes all that information, that all the ROS2 topics and everything, and then uses WebSocket to forward it to this port. And the main purpose of this is to be able to access that information remotely. So right now it's not super useful when running locally. However, as we'll see later on, you can use this WebSocket to connect to and get debugging information from ROS that's running on a server on your local machine. So we'll start the bridge as well. So that's running. So we should, if we do Docker here, we can see the Foxglove bridge is running, and then our talker and our listener are running as well. Then lastly, we can actually run Foxglove Studio from Docker as well. This is actually the UI and user interface that we can use to view stuff on. So we're going to run that. Again, we can see all 4 of these services are now running. And then if you go to a web browser, you can go into localhost 8080, and this is running that Foxglove Studio server on that Docker container we just ran. And so now we're going to open a connection. We're going to do this to the local WebSocket that you saw that the bridge was mapping everything to. We're going to go and open, and then you can see there's some ROS topics here printed out. And we have chatter right here, and as you can see, the data is being updated in real time. You can see the values changing there as it's coming in. And so that's just a very basic example of how to set up and run Foxglove to get the ROS2 topics and information visible here. So now we've covered essentially all the individual components that we need to know about: Docker, Docker Compose, ROS with Docker, CARLA with Docker, and then Foxglove. And so now we can actually run and execute the simulation stack as a whole. So we're going to go now back to the top level folder. And for reference going forward now, we're just going to reference in this top level README under the section 2.0 development, we're going to reference all the notes that are listed in here. Now, if we go to our project here, and then we can open up this Docker Compose file that's listed here. And so this is a combination of everything we talked about. So this Docker Compose runs a CARLA server. It runs the CARLA ROS bridge, which, as we described before, essentially transcribes the CARLA messages into ROS topics. We run that custom ROS2 container, just prints out the topics available. We can run a CARLA node, which is a special node. It's essentially just a container with a Python built on Python Alpine with the CARLA API installed, and it can use the CARLA API to interface with the CARLA server that's running to spawn objects and agents and all that sort of stuff. And there's a Foxglove bridge, which, as we mentioned, is to map all this data, all the ROS data onto the WebSocket so it can be accessed remotely. And then we're also just running the ROS listener and talker as like some examples of more nodes running together. So this overall defines the simulation stack. The main components are the CARLA server, the ROS bridge, the ROS2 container, and then the Foxglove bridge. So those are all the main components together. So if we just leave here, let's just go back to here. And so, oops, sorry. And so, yeah, I just covered what the project structure here is. Now, that compose script is defined at the top level of the directory here. And then as you can see in the Docker folder, we have specific subfolders for the CARLA client, the Foxglove bridge, the ROS2 container, and the ROS bridge, because we're all building custom images for each. And then the Docker compose we just opened at the top is what runs and executes all of these together in one command. And as mentioned before, as you saw before, this is the architecture it follows, as you can see here. And so now we're going to actually go about deploying it. Now, first we're going to deploy locally. And we've already kind of covered how to deploy using Docker Compose. One thing I'll note is that the first time you run this, it'll probably take quite a while to just actually set up and run, because there's a lot of large images that you need to download and build. And just to be safe, you probably need about like 30 gigabytes of space in your system to run. So just keep that in mind as we go here. I've already done this also, it shouldn't take long for me, but just when you do this on the first time in particular, just keep that in mind. And so with that, we're going to go here, and now we can just do run Docker Compose. And we'll just do it in attached mode. And we'll just give that a few seconds to build and run everything. And through the magic of editing, we're back. So it took a while for mine to build just because I kind of forgotten that I had removed all the containers locally as a cleanup before this. But in any case, here we are and we are running, and there's a lot going on. A couple things I want to note is when you run this, one, the first time you do, it will take a long time. The second is make sure you let it run just uninterrupted for at least a minute or two, as because there are some known bugs with how certain components initialize right now, and you just need to let it do its thing, and then it should be fine. You should be seeing something similar to what you're seeing right now. And I'll discuss those bugs and things later. They're noted down in the READMEs. But for now, once you've run this and you've given it some time, you should be seeing something like this as logs. So as you can see, ROS container is printing out a ton of topics. You should be seeing that there's a ton of CARLA topics here, as you can see, with a bunch of different information. Then the ROS bridge is printing out a bunch of stuff about skipping frames and whatnot. The warnings, just don't worry about that too much. Just things are not set up optimally right now, let's put it that way. It's just more of a demonstration. And then you can see the ROS talker, ROS listener also printing it out. So you can see all this stuff going on. And if you, sorry, give me a second here. You can print everything out using this command to format everything nicely, since there's a lot of services going on. So, and this is in the README, you can copy that from there. If you print this out, you can see everything that's currently deployed. So you can see the CARLA client, Foxglove bridge, ROS2 container, the CARLA ROS bridge, the ROS2 listener, talker, the CARLA server, Foxglove studio, and these are actually from before, from a previous administration. And so I can see everything that we've talked about running is running, and it's still going here. And then also we can run Docker stats here. And you can see everything being executed. As you can see, CARLA server takes up a lot of computation, same with the ROS bridge and the client as well. because these are running a bunch of stuff. And don't be too alarmed at the CPU percentage being over 100, just because this is spread across all the CPUs and everything. So yeah, it's not a super big of an issue as it stands right here. But yeah, you can see the statistics here and everything running, and that is most of it. And then, as before, if we navigate, oops, wrong one. If we navigate to a web browser and we go into localhost, here, and then we can open a connection to our this WebSocket, and there. And we can see all the topics and stuff previously discussed are visible here. So there's a bunch of them. You can see all the CARLA topics here, visible and everything. And so this is all that information being streamed. And that is all there is to it. So we'll just shut this down, and that is that. So lastly, we're going to walk through how to deploy and run the simulation stack on some remote server. So for this demo, we're going to just use the autonomous server cluster. And as a quick reminder, if you haven't configured that locally, in the top level README in the repository under the autonomous section, there's some instructions on how to set up a remote server. So in any case, we're just going to SSH into the server. Just cd into the project, and we're in here. And then now let's just run Docker Compose. It's that straightforward. I'm actually going to add some additional flags here just to make sure that, as I've been running this a few times, no lingering containers or anything conflict with this. Just going to rebuild a little bit. And there it goes. It's starting to run. So we'll just give it a little bit of time to build and run. And as I said before, there's some bugs currently right now while this initializes. So you just have to give it a little bit of time to fully get set up and configured. But in any case, here we are. And this is looking similar to what we had before when I was running locally. You can see all the ROS topics being printed out, all the CARLA ones, the ROS bridge debug messages, and then the talker and listener, for example, running. So now we have this running on the remote server, but I want to be able to get the data from it and view it locally, for instance. And we're going to use Foxglove as we did before, but this time it's going to come into use with that remote connection. So to do this, you want to go into another terminal, and you're going to want to run this command here. That's essentially going to bind this port to a different port locally from, so the port that WebSocket is streaming on the server, which is 8765, to the localhost port 5900, and then you can view the WebSocket information there. So if we run this, just give it a second, it's connected. Now we can go over here. We can open up, this is assuming you have Foxglove Studio running in the background, which I still do. So we can go here, we can open up connection, and then we're going to change this to that port that we specified there before. And now if we run open, there you go, it's connected. And so this is all that information coming from the server. So, and just to illustrate that, I'm going to open up in their terminal here, Docker plus, and yeah, you can see Foxglove Studio is running, but there's nothing else. There's actually a talker and a listener, but that's there's no CARLA. You can see on the simulation stack is running locally for me. If we go SSH to watch a server here, Docker plus here. You can see all the there's a bunch of stuff running here as well because this is on a remote server, so it shares. There's other things running for other people, but you can see we have our stack of containers running here on the remote server. And so that's how you can access the information and run the cluster on a server and access all the data and logs locally. Now, just a quick word of caution. When you're using a remote server like this, is sometimes there might be other services running to use the same port, and it might create conflicts and whatnot. And so just to show what that looks like, we're just going to stop this here. Okay, I don't know why it's not exiting. Just there we go. Okay, going to let this finish stopping first. While we do that, I'm going to go and change. So I'm going to change my config here to use the different host than what I was using there. Now let's exit. And now let's SSH into a different specific host on that server cluster. So this is different than the one I had before. And you can see I still have the same project here, run Alice in here, everything's the same. But now I'm going to try and run Docker compose up. And you can see I get this error on the Foxglove bridge, and it's talking about how the bind for that port is already allocated. And if I run Docker here, I believe you can see that this service here is actually using that port, as you can see. So just a word of caution that if you see this error, it's likely because some other service is running using that same port and it's in conflict. So the easiest fix is to just hop over into a different host, run it there. If this is someone else's service, or just ask them to take it down or something, or change what port you're using. So that is that. And with that, that should cover everything you need to know for running this and running a simulation stack. So as I mentioned before, just to do a quick summary in this repo, the workshop has a transcript essentially of everything we covered, and it has some examples here provided. It has a slide that we started off attached as well, and then everything else we covered near the end of deploying this whole stack. The top level README documentation available here walks through everything, how to install, and even talks about some of those bugs I mentioned before. So be sure to reference those for further information. In any case, I hope this has been helpful, and if you have any questions, feel free to let me know.